Let's now turn our attention to linear functions. So linear functions are named that because when you map out the points in a linear function, when you graph these points, they're always going to draw out a line. Now that line could be horizontal, it could be vertical, or oblique. Oblique meaning that it is slanted in some way. But in two dimensions, those are your only options. And all lines, all linear functions, that is, are going to have equations that can be expressed in the form ax plus by equals c. And that's called the general form for the equation of a line. And the general form is good to know to be able to recognize that you're dealing with linears, but we don't really work often with the general form directly. There's other forms that are much more useful to us. Now, let's talk about the edge cases first. So the simplest cases of lines, that is, and that's the horizontal and the vertical lines. And it's really important to be able to identify which is which when it comes to working with graphs and equations. And if you don't know these, if you mix them up, if it's always just like a guess as to which one's which, you need to get past that. You need to absolutely just know these. All right, so if you're working with a horizontal line, of course that's going to be a line parallel to the x-axis, but its equation is y equals some constant. And if you're working with a vertical line, that's a line that's going to be parallel to the y-axis, and its equation will be of the form x equals a. So, for instance, if you have a horizontal line, let's say it's just like y equals 2, for instance, then this might be what it maps out as, all right? Parallel to the x-axis, as I said. And then, for instance, if you have a vertical line, let's say you have the equation x equals -3, then it's going to look something like that. And it's really good to understand this because there's a lot of just subtle understanding in mathematics and equation solving when you understand that when you solve an equation, you're often solving not for a single point, but you're solving for an entire line, and that line is actually a vertical line. When you solve an equation, you often end up with something of the form x equals a constant. So it's really good to understand and picture and imagine that as a vertical line rather than just a single point. So you can think of it as just a single point on a number line, but in two dimensions, you might want to think about stretching that out as an entire vertical line. All right, now oblique lines, those are the ones that are slanted. And the thing is, you can't express a slanted line as just x equals something or y equals something. That's when you need a little bit more. And so in that particular case, you might have something like y equals, say like in this case, this could be like -x plus 2, for instance. All right, and that right there, that would express the relationship of the different x values to the y values that show up on this line. And that's the kind of equation that you probably most recognize when it comes to linear equations. That's the one that we generally talk about the most. It's called the slope-intercept form of our lines. M, the number that's multiplying x, that's going to be the slope of the line, and then b, the constant value, is the point where the line crosses the y-axis. Slope, it's good to understand how slope works. Slope is defined as the ratio of vertical change to the horizontal change. So when I say ratio, I mean division. So mathematically, we express that with this formula right here. So the slope of a line looks like this. Now, m equals y2 minus y1. That's the change in the vertical direction. X2 minus x1, that's the change in the horizontal direction. And where that comes from, just so you fully understand, if you have some line and you pick 2 points on that line, and it doesn't matter what points you pick, all right, when you go from one point to the next, if you don't follow the line, if you follow the horizontal and vertical changes, The vertical change, if this is the point, say x2, y2, and this is the point x1, y1. The vertical change is y2 minus y1, so how much change happened in the y direction. The horizontal change is the change in the x direction, so x2 minus x1. And if you take the ratio of those two, that gives you basically like an average change. But it measures the direction of the line, and that's what we define as slope. You've probably also heard this as rise over run, and that's what these changes are. So it's the rise from one point to the next divided by the run of one point to the next. And understanding that, we can actually come up with another line equation, which is extremely important. And of all the line equations, this is probably the one to know the most. This one right here is called the point slope form. And it allows you to take some point on the line and a slope, put those together, and come up with the equation of the line. And you can sort of do that with the slope-intercept form, but you have to know the y-intercept as the point. You're not allowed to just have any point out that exists on the xy axis. It has to be the y-intercept. But this gives you a little bit more freedom. As long as x1 and y1 is some point that exists on the line, and m is the slope of the line, we can use this to come up with the equation of a line. Now in the end, we very often express it in the form y equals mx plus b. But you have to understand, you start here, and you end here. All right, so that's always the way we generally do things. All right, so for instance, using the point slope form, let's find the equation of a line passing through the point 2, negative 4, having a slope of 1/2. All right, so visually, what's happening here is we have some point which is at 2, negative 4. So 2 on the x, 1, 2, 3, negative 4 on the y. So it's passing through this point, and it has a slope of 1/2. And the slope of 1/2 is going to be, you would go up 1 and then over 2 to get to the next point. So that means my line kind of looks like this right here. Now here's the thing. There is a y-intercept. All right, it's probably at negative 5, but we don't really know that from any of the given information. We'd have to determine that. And if we did, we could directly say, oh, the equation of this would be y equals 1/2 x minus 5. But if we don't know what that y-intercept is, we can't use the y equals mx plus b formula. Now, there are students who do this, and what they will do is like solve for b. You can do that, but the point slope form solves for b for you. All right, so it's kind of designed to do everything all at once. So this is how I use it. It's going to be y minus the y coordinate of the known point equals m, which is 1/2, times x minus the x coordinate of the known point. And then just algebraically simplify here. So 1/2, this would be distributing the 1/2. So 1/2 x minus 1. If you say subtract 4 from both sides, then what you end up with is y equals 1/2 x minus 5, just as we expected, but we had to sort of guess at what that would be by coming up with a graph first. And you don't always want to come up with a graph to try and guess at what that's supposed to be. It's just, this is the easier way of doing things. All right, find the equation of a line passing through the points 2, negative 3, and 1, negative 5. All right, so again, and you don't have to visually do these things. I'm just doing this so that you can see through this review exactly what it is we're doing. So 2, negative 3, that would be 2 this way, negative 3 this way. There's 1 point. Negative 1, 5. So that should be right there. So my line should be, approximately this line right here. So I'm not exactly sure what the slope is. It looks like the y-intercept's probably at -2, but maybe, I'm sorry, at +2, but maybe it's at 2.5. It's hard to really tell unless you get out, a ruler to kind of really measure these things off correctly. But what we can do is first determine the slope by using the slope formula. So you take y2 minus y1 over x2 minus x1. So that would be 8 over -3. So I'll just say -8/3. And then plug into the other equation, the point slope form. So y, and you can use either point at this point. It doesn't really matter. I'll use this one since it comes first. Y minus -3 equals my slope of -8/3 times x minus 2. So this would be y plus 3 equals -8/3 x and plus 16/3. Then I'm going to need to subtract 3 here. But when I subtract 3, I've got to add it to something that's in thirds. So I'll go ahead and convert that and make it 9/3. So that gives me y equals -8/3 x. 16 minus 9 would give me 7, so that would be plus 7/3. So with the result like this, you can clearly see that guessing at what it would have been, like if I guessed it being at 2, I wouldn't have had the right values because my graph just certainly isn't accurate enough to show that the point is not at 2, it's slightly above 2, it's at 7/3. So it's always best to be comfortable with the algebra involved in doing these things, and at this level, you should be comfortable with that algebra. If you need to practice at this point, do that practice, but you need to be comfortable with these kinds of things. Working with line equations, you will do a lot of this throughout calculus. All right, another concept that's often discussed with lines, which isn't always useful in calculus, but it's good to know, parallel lines and perpendicular lines. Parallel lines have the same direction. Slope measures the direction of the line, so what that would mean is you have two lines that have the same slope. Perpendicular lines, it's actually a little bit more difficult to show. You can do that with trigonometry, but I'm not going to go through the details. It suffices to know that if your slopes are negative inverses of each other, then you have parallel lines. So that's just a good fact to remember there. All right, that's everything that you would really need to know about linear equations. Quadratic equations are the next thing that's really important in a calculus class to make sure you can adequately work with here. Now, there's not nearly as much in terms of graphing, but for the most part, being able to solve quadratics, that's really the most important skill that you need to be able to do. And this is often a stumbling point for students. I still find at this level students having skills that are below what I expect in a Calculus 1 class in terms of solving quadratics. And if you find yourself in that particular camp, then you need to get some practice. You need to get that understanding because it's a skill that can kind of make or break your success in calculus. So quadratic equations, these are equations that can be written in the form ax squared plus bx plus c. So the most identifying feature is that you have one variable. So the only variable here is x. A, b, and c are considered constants. And the highest degree on any of those variables is 2. All right, so a linear equation, the highest degree is 1, and a quadratic, the highest degree is 2. So we can often solve these by factoring, and your skills in factoring need to be quite good at this level, okay? But occasionally you might run into a situation where you need more advanced methods, such as completing the square or the quadratic formula. All right, let's talk about factoring to start with. So this is all based off of what's known as the zero factor property. And it's a really straightforward principle in mathematics. And it says that if a times b is equal to 0, then either a is 0, b is 0, or both are 0. That's the only way to get a product of 0, is that if one of your factors happen to be 0 as well. And this doesn't apply to any other value. Like there's no 6 factor property. So if you try and say if a times b is equal to 6, then that means that a is equal to 6 or b is equal to 6. It doesn't mean that, because you could have a is equal to 2 and b is equal to 3, and that would mean the product is 6. And neither of those are 6. So you're only guaranteed that this works when it's set equal to 0. And when you're solving quadratics, one of the first steps you always have to take is set the thing equal to 0. And that's exactly why, because of the zero factor property. So let's solve a couple of quadratics together. Now these should factor. Let's see what happens here. So x squared minus 2x minus 8 equals 0. Now there's two different types of factoring that you're going to need to be able to do. The first is absolutely critical. All right, you have no excuses not to be able to do this one. That's when the leading term coefficient is 1. The leading term coefficient is the value multiplying your x squared term. Now, when that's the case, all you need to do is set up two sets of parentheses. The first value in those sets of parentheses are both x and x, because those multiply together to give you x squared. That's the only options there. If it factors into integers, that is. Now, 8. Now you just need to come up with two numbers that multiply together to give you 8. So it could be 1 and 8, it could be 4 and 2. I generally find, though, it's usually not the extreme pairs, like the 1 and 8 would be the extreme pair. It's usually the middle pair where the values are kind of closer together. So I'm going to start guessing with 4 and 2. What I need is this middle term to work out. So just kind of think of FOIL. When you FOIL two things, like if you have x plus 2 times x minus 4, for instance, you multiply the first two together to get x squared. You multiply the outer two together to get minus 4x. Then the inner two together to get plus 2x. And then the last two to get negative 8. These middle two add up. And so you have to make sure those middle two add together. So we've already made sure the x squared and the negative 8 work. That's why we chose the x's and the 4 and the 2. The middle term is what matters next. Now, this needs to be a negative 2, so I need the 4 and the 2 to add up to negative 2. So that would be, that's a minus and that's a plus, and that's going to work great because that would be x squared plus 2x minus 4x, which gives me negative 2x, and then 2 times negative 4 is negative 8. So that works great. Now, the next piece here, this right here, this is one number, okay? And I mentioned this in the last review video with the bubble charts. So it's an expression which represents a single number. And that's really important to kind of understand here. I know that you can see a variable x and you can see the number 2, and you might say to yourself, well, that's two numbers. Once you define a value for x, it's going to evaluate to a single number. It's one single y value, okay? So this just tells me how to map from an x value to a single y value. So this is one number, and this is another number. So I have two numbers. When I multiply them together, their product is 0. It's equal to 0. So if the first, that means according to the zero factor property, that either the first number is 0 or the second number is 0. Or it could be both. And we don't know which one's which, so we just assume, the possibility that, it's either one. It doesn't really matter. Which tells me that x is -2 is a solution, and x equals 4 is a solution. So -2 and 4 solve that equation. And notice, x equals 4. That's the form of a vertical line. So if you were to look at this in terms of a graphic solution, it's saying that there's a solution that happens along this this vertical line at x equals 4. Now, we also kind of happen to know in this particular case that the y value is 0. But that's not always going to be the case. There's applications where the y value isn't necessarily 0. But in this case, it is. It doesn't matter really. It's just telling me the x location of this is 4. Then you can figure out what the y is later from that point. But it happens along a vertical line. All right, let's try this next one. So first off, this thing is equal to 6. That's no good. We don't have a 6 factor property. We have to first bring the 6 over and have it set equal to 0. So if I subtract 6 from both sides, that's -5 and equals 0. Now I need to factor. Now this is the form where things get a little bit tougher because the leading term coefficient is something other than 1. When that's the case, there are more possibilities for solution, or potential factors, I should say, and so you have more possibilities to try. But it's not impossible. Now, there's all kinds of different ways of doing this. I've seen, methods using like a box method where you put everything off to the side and try and do everything inside of a box. I've seen methods of splitting up the middle term into two individual values so that you can use factor by grouping. There's lots of different ways. But I honestly think the easiest and simplest is just the guess and check method. All the others rely on guess and check in some way. So it's not like you're not doing guess and check. It's just it looks different a little bit than guess and check. But regardless, what you need here are two things that multiply together to give you 2x squared. And really your only possibilities are x and 2x. Because again, you're doing reverse FOIL. So you need two things that are going to multiply to give you that first term. So x and 2x multiply together when you do the first two to give you 2x squared. Now you need two things that are, in the last part. So if you do 1 and 5, you want those to be able to multiply together to give you the -5. All right, so when I multiply these together, I get 5. But what I need in addition is the middle two to work out. So like 1 times 2x is 2x. X times 5 is going to be 5x. And I need these to essentially add up to -3x. So if that's negative and that's positive, that's going to work out. So that tells me that should be negative and that should be positive. And this should work just fine because if we check everything again, x times 2x is 2x squared. X times -5 is -5x plus 2x. When I add those terms together, I get -3x. X times -5, 1 times -5 gives me -5. That's great. It's perfect. So that solves it. Now, that is the more difficult case, but you can't just say to yourself, oh, that's hard for me, I'm just never going to do those, and then just skip them. Because they're going to show up, and you need to be able to solve these things. And with practice, it does get easier. But I understand that it is the more difficult of the two cases. And once you get to this point, it's the same from the next step. You just say, okay, I have two things, two numbers that multiply together that give me 0. That means that the first number is 0 or the second number is 0. So solve both of them. That gives me x equals -1. 2x equals 5, so x equals 5/2. So that right there, those are the two solutions to the original equation. Now, one thing I want you to see about this, I want you to see this visually happen. All right, not so easy to see the visual solutions in the previous one, but here I think it is a bit easier. All right, so hopefully I won't get any problems trying to graph these. Let me see what I can do. Okay, so 2x squared minus 3x plus 1. So let me put that on a graph. All right, 2x squared minus 3x plus 1, I think it was. Then my other side of the equation was just 6. Okay. So y equals 6. Now, when I'm saying I'm trying to find the solution of these two, what I mean is I'm trying to find where these two graphs intersect one another. And so you can kind of see here where they intersect. It looks like -1 over here, and then +2, oh, sorry, at, somewhere between 2 and 3 over here. But the values that I've come up with, if you'll note, those were, this one here, those were -1 and 5/2. So let me go over and graph those as vertical lines, because they are vertical lines. So x equals -1. If I graph that one, it's okay. It wasn't graphing in the regular mode of just x equals -1. That's okay. I can switch and graph it in parametric mode. So this is don't worry about what you're looking at right here. It's a parametric equation for x equals -1, which, as you can see, passes right through that point. So it's saying that the solution to this equation happens somewhere along the line x equals -1. And the other x equation was, the other solution was -5/2. And so somewhere along, oh, actually it was +5/2. Somewhere along +5/2, we'll have the other solution. So let's see if that makes sense. And when I graph that, you see the intersection of these two curves along that vertical line, which is what the solution to this equation predicts. Okay, let's go on to other ways of factoring. So coming up with the solutions, that is, we have factoring is probably the most used method. Now, the next method that you need to be comfortable with is completing the square. You're not going to use it all the time probably, but it's a technique that you want to be familiar enough with that you can do when it is necessary. It allows you to solve any quadratic equation. So factoring only works if your solutions happen to be integer or if they happen to be fractions. If they have square roots or if they're complex, then factoring doesn't do anything for you. All right, when you are completing the square, one thing that you need is, first off, the leading term coefficient to be 1. And it's best if the middle term, so the term that's multiplying x, is an even value. That just prevents any kind of fractions throughout. And that's sort of how I determine if I'm going to use completing the square or if I'm going to use quadratic formula. It usually comes down to if that middle term is even or odd. But this is the process. If that leading term coefficient happens to be something other than 1, then just divide everything through by the leading term coefficient. Make sure it's in the form x squared plus bx equals -c. So normally when factoring, we want everything equal to 0. But we're not using the 0 factor property here. We're using a different concept. So it's okay that it doesn't equal 0. It's going to be whatever that constant happens to end up being. Now, there's this seemingly magical term, which is half of the number multiplying x squared. And that's the key thing to remember here. You're going to take that value and just add it to both sides. And what that does is it creates a perfect square trinomial on the left-hand side of your equation. And when you have a perfect square trinomial, then you need to factor that. All right, when you factor that, you can solve the remaining quadratic using what's called the square root method, which is just basically you have the square of an equation equal to a constant, so you just take the square root of both sides in order to solve. So you don't really need any kind of factoring or anything from that point. All right, let's take a look at some examples here so you can see how it's done. Now, the first one, what I have here is the leading term coefficient's already 1. That's great. The middle term is even. That's really good. All I need to do for setup is just move that 11 to the other side. All right, now, the magic term. So if I take the b term, which is 8, divide it by 2 and square it. So 8 over 2 is 4, 4 squared is 16. I just add 16 to both sides of the equation. And that makes this right here a perfect square trinomial. And what I mean by a perfect square trinomial is that it's of the form a squared plus 2ab plus b squared, which factors into a plus b quantity squared. So it's just the square root of these outer two terms added together. Well, the square root of x squared is just x. The square root of 16 is positive 4. So then that's what it's going to factor into. You're writing it in that form so that it turns into a perfect square trinomial, so that it factors easily like this. All right, now negative 11 plus 16 is 5. And to finish off, you just solve this equation. So you have a perfect square equal to a constant. Just take the square root of both sides. Now, you do have to consider the plus or minus case for the square root because of variables involved, but that's the only complication here. So x plus 4 equals the plus or minus square root of 5, which means we have x equals negative 4 plus or minus the square root of 5. And that's not a lot of work to get a fairly complex answer here. We would never have been able to come up with that through the process of factoring. All right, let's try this again. So y squared minus 12y plus 26. I'll write it y squared minus 12y equals negative 26. And then the magic term, I take negative 12 divided by 2 and then square it. So that's going to be negative 6 squared, which is 36. So I add 36 to both sides. This, on the left-hand side, is a perfect square trinomial. It's just the square root of the first term and the square root of the second term. Although, sorry, this should have been a minus because it kind of takes the sign of this number right here. All right. Now, on the other side, negative 26 plus 36 gives me 10. So that means y minus 6 equals the plus or minus square root of 10, or y equals 6 plus or minus the square root of 10. And that's it. We're done. That's completing the square. Definitely a technique worth knowing. It really just comes down to understanding how to get this magic number, and it's just a really quick formula. B over 2 quantity squared. Now, the quadratic formula. The thing about the quadratic formula is if you take the general quadratic, which is ax squared plus bx plus c equals 0, and you apply completing the square to it, it'll eventually suss out and give you this equation right here, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So it comes to us, it's sort of just a result of completing the square. So without completing the square, there would be no quadratic formula in the first place. But it's really good to use, especially when this middle term is going to be complicated. So like for instance, if I start using complete the square on this equation, I would have 2x squared minus 5x equals negative 1. And you have to have the square term with a coefficient of 1, so I need to divide everything through by 2, which gives me x squared minus 5 halves x equals negative 1 half, which I can absolutely do complete the square on, but that magic term is 5 halves divided by 2 quantity squared. It ends up as a fraction. You're going to be adding and subtracting fractions throughout. It just gets more and more kind of complicated because of the fractions. So I tend to not use completing the square when that sort of thing occurs. That's when I use the quadratic formula. So it's negative b. All right, b in this case is negative 5. So that's going to be the opposite of negative 5 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this would be 5 plus or minus the square root of 25 minus 8 all over 4, which is 5 plus or minus the square root of 17 over 4. And that's really not that bad of a result, given the complexity of the solution. So it's not really something that is, I tend to go toward first, the quadratic formula, that is. And the reason for that is because students tend to make mistakes with the quadratic formula in general. Oftentimes this square root bar kind of shrinks along the way, or there's some arithmetic error along the way. So there's often problems with the quadratic formula. I find that students do much better with factoring in the completing the square process, and so I always recommend do those first, and then reserve the quadratic formula for when it's absolutely necessary.